Good morning, everyone. First of all, let me introduce myself. My name is Nina Widiawati from Batan. I'll be responsible for hosting today's event. Before we begin the webinar, I would like to request your attention to the following protocol. The webinar will be conducted in English. All microphones will be mute except for the speakers and moderator. The discussion session will be held at the end of each presentation. You may use the chat feature to ask questions. Materials of the presentation will be available at the attached link. And please register your attendance via the link provided during the webinar to receive the certificate from the organizer. And the webinar will be broadcast live on the Humas Batan YouTube channel. To begin with, we have Deputy Chief of Mission of Embassy of the Republic of Indonesia in China. Here with us, distinguished Mr. Dino R. Kusnadi. Welcome to the webinar, sir. And welcome to the Honorable Mr. Suryantoro as Deputy for Nuclear Energy Technology Batan. Also, Mr. Xie Jiejie as President of China Zongyuan Engineering Corp, CGEC. Mr. Ding Jian as Vice President of CGEC, and also Mr. Dandang Purwadi as Head of Center for Nuclear Reactor Technology and Safety Batan. And we have all speakers today, Dr. Suparman from Batan, Mr. Sun Jun from Tsinghua University, Mr. Chen Bin from Synergy, Mr. Jiang Huixia from China Nuclear Power Engineering Corp, Ms. Hou Yani from China Isotope and Radiation Corporation, Mr. Cheng Wei from China Institute for Radiation Protection, and Dr. Sun Ziong from China Institute of Atomic Energy. And also moderator, Mr. Huang Yuliang from CGEC, and Dr. Saiful Bahri from Batan. And representatives and participants from National Research and Innovation Agency of Indonesia, BRIN, and all guests and audiences. We're delighted to welcome you to the international webinar on nuclear power and technology. The webinar is organized by the CNNC and National Nuclear Energy Agency of Indonesia, Batan, and also to commemorate the 26th anniversary of the National Technology Awakening Day or Harteknas of Indonesia. To begin with, I would like to welcome President of CGEC, Mr. Xie Jiejie, to give the welcoming remarks. Your floor, President.
Okay, thank you very much. Dear Mr. Dino Kusnadi, Mr. Suryantoro, ladies and gentlemen, dear friends, good morning. Nice to meet you all through video links. To begin with, I would like to express my sincere gratitude to Mr. Dino Kusnadi, Chairman ENHA, Mr. Suryantoro, Mr. Purwadi, Mr. Superman, and all colleagues of National Research and Innovation Agency and Batan. Your strong support and strong coordination and support has enabled the successful holding of webinar against the ravaging coronavirus. On behalf of CNC, I would also like to thank all the experts for your time today and extend my warmest welcome to all of you. Indonesia is the largest in terms of GDP and population among Asian countries. As its nuclear industry started earlier than other countries, Indonesia has accumulated fairly rich experience in nuclear energy research. The driver of Indonesian manufacturing industry has been set as high-tech in recent years. Nuclear energy is clean, stable, safe, and efficient. Its unique advantages will contribute a lot to Indonesia's economic growth and local employment. For example, a nuclear power unit pools the construction and manufacturing resources of hundreds of enterprises. That begins that brings tens of thousands of jobs and consequently lifts the industrial chain development of high tech. During his visit to Indonesia in October 2013, President Xi Jinping has proposed to build the 21st century maritime Silk Road, which highly fits Indonesia's vision of global maritime fulcrum and will help usher in a new stage for the bilateral relations. During President of Indonesia Joko Widodo's visit to China in March 2015, China and Indonesia signed the joint statement on strengthening comprehensive strategic partnership between the People's Republic of China and the Republic of Indonesia. Multi-level and wide-ranging energy cooperation between both countries has been enabled thereafter. Since then, CNC has been promoting and implementing the nuclear energy cooperation with Indonesia proactively, thanks to the strong support of Batam, government bodies, enterprises, and educational institutions from both countries has made multiple mutual visits, signed several cooperation documents, and conducted technical exchanges and training. All have encouraged the steady development of our nuclear energy cooperation. In 2016, Batam and CNC signed the joint project agreement for the HTGR development program, which further deepened the cooperation on nuclear energy and gave rise to new prospects. CNC is one of the few nuclear power majors in the world to boast a complete nuclear industry chain and over 30 straight year experience in nuclear power construction. The year 2021 has seen multiple achievements by CNC in nuclear power engineering and construction. Unit 5 in Fuqing Nuclear Power Plant, the first project to adopt China's homegrown HPR 1000 technology, started its commercial operation on January 30, 2021. The same progress was made by the first HPR 1000 unit overseas on May 21st, namely Unit 2 of Karachi Nuclear Power Plant, Pakistan. They together set the record of the shortest construction period among Generation 3 units in the world. China's first homegrown SMR ACP 100 demonstration project started construction in Hainan, China on July 13th this year. I would also like to convey the encouraging news regarding HTGR. The technology for our cooperation, the Shidao Bay HTGR demonstration project, is progressing smoothly in China, with its fuel loading completed this month and grid connection expected by the end of this year. It is the only HTGR project under construction in the world. CNC has extensive experience in other fields, including nuclear technology application, nuclear irradiation protection, and research reactors. We have invited experts of these areas to share their ideas and expertise in the webinar. We also hope to share CNC's advanced nuclear power technologies and experience in developing a complete nuclear industry chain, enhance mutual understanding and trust, so as to lay foundation for our further communication and cooperation in nuclear energy. The Chinese government has made it clear in September 2020, the carbon peak and the carbon neutrality will be achieved respectively by 2030 and 2060. Nuclear power is sure achieve the goal The conservative estimation shows that the new nuclear power units will be doubled in China based on existing units. Such scale of nuclear power development is unseen in any part of the world at the present. The scale will also entail the growth of China's nuclear technology, construction, innovation, integration of global nuclear supply chain, and the cultivation of highly skilled nuclear talent team, and consequently improve China's nuclear energy strengths. China is sure to becoming the world leader in nuclear power development. As the platform specializing in the globalization of CNC's whole industrial chain, CZAC is dedicated to providing a one-step solution for our customers in the world. With its rich experience in nuclear energy project development and infrastructure investment. Given the broad prospects of Sino-Indonesian Nuclear Energy Corporation, CZAC hopes to work with Baton and other Indonesian nuclear energy stakeholders to boost the construction of Belt and Road initiatives and Indonesia's vision of global maritime fulcrum, so as to embrace a bright future for Sino-Indonesian Nuclear Energy Corporation and benefits the people of both countries. I sincerely wish the COVID-19 will end soon. I would also like to invite all of you to visit CNC's nuclear facilities when the pandemic is over, and looking forward to visiting Indonesia to conduct more in-depth communications and cooperation in nuclear energy with you. Finally, please accept my sincere appreciation of Baton's great support and cooperation for this webinar. I wish the seminar a huge success. Thank you all.
Thank you very much, President of CZEZ, Mr. Xie Jiejie. Now we would like to invite the Deputy Chief of Mission of Embassy of the Republic of Indonesia in China, Mr. Dino R. Kusnadi, to give welcoming remarks. Give you the floor, sir.
Thank you for the MC in providing me the opportunity. Allow me, Your Excellencies, Mr. Xie Jiejie, the President of the China Songyuan Engineering Corporation, Mr. Suryantoro, Deputy for Nuclear Energy Technology dari Badan Tenaga Nuklir Nasional, Dr. Suparman, Head of Center for Assessment of Nuclear Energy System, Batan, distinguished speakers, participants, ladies and gentlemen, a very good morning to all. Allow me first of all to extend a warm greetings from Ambassador Johari Oratmangun. He presents his kind, warm greetings to everyone. It's unfortunate that he's currently have another engagement to do so, and I'm representing on his behalf. Indeed, the embassy is, I think, very supportive of this discussions between Batan and also the CZEC regarding collaborations in the field of nuclear technology. You, Mr. Xie, in your address mentioned about the current relationship between China and Indonesia, which is not just close, but also more and more getting stronger. Allow me also to say a few words regarding the bilateral relations with Indonesia. Mrs. Xie mentions about the comprehensive strategic partnership that Indonesia and China has a foundation on, which was started in 2013, which was an upgrade from the previous collaborations of strategic partnership. In 2013, we became a comprehensive strategic partnership. These three words, strategic, comprehensive, partnership, has a very strong meanings to it. The first, of course, is the partnership means that there's equality and there's a close friendship, also trust that exists between China and Indonesia, which is also continually growing. Comprehensive means that it's not just about one avenues in collaborations, but encompasses a lot of avenues in political, security, economic, investments, social, cultural, but also including the energy sector. And this is also part of it within the nuclear technology sector. Mr. Xie also wisely mentioned about the collaborations that we have between the Belt and Road initiatives with the vision of the Global Maritime Fulcrum of Indonesia. This also has a very high intensity collaborations going on currently, and it's also growing stronger and stronger day by day. Not just that we have an MOU in the synergy of the BRI and the Global Maritime Fulcrum, but also exist corridors of cooperation. And these corridors of cooperation, there's actually 4, is not just based on those sectors, but also are welcome to new sectors and new collaborations. So this endeavor that we are now doing so between the CZEC and with Batam has all these mechanisms already below them so that this can grow further and with a very strong foundation. The future of China and Indonesia relations continue to grow stronger. My ambassador cannot emphasize this more clearly. We are China is Indonesia's strongest trading partner. The value is almost reaching $80 billion in trade. The balance is getting closer to almost a balanced part. Our deficit is now about 4 billion compared to almost 14 2 years before that. So again, this shows the close partnership that we have with China and Indonesia in the trade sector. Investments is also very strong. The needs of Indonesia for upstream industries, but also how to develop our minerals and so forth, has been collaborating with China to give that added value. And if I can stress the word added values, our relationship with China has always been that China has given Indonesia more values, more added compared to other offers that we've had. And in this case, I may say that it fulfills also the priorities of our government. President Joko Widodo mentions in his inaugurations for his second terms that Indonesia seeks for a better human resources development, that we can also have a more closer transfer of technologies to build Indonesia's infrastructure, and also to increase further collaborations in research and developments. Now, in all other fields, China has aided Indonesia's in this collaborations in partnership, and I do hope that in this endeavor that China will also continue to give added value in this relationship so that it will benefit both sides. And I'm sure and very confident that we will achieve this. And that's why this webinar is very pertinent and important. Ladies and gentlemen, Bapak dan Ibu sekalian, let me close my introduction that I do appreciate the cooperation, the existing cooperation and communication established currently between Batam and CNNC, but also with CZEC, especially existing visits that you had before the pandemic. That's why webinars such as this needs and is pertinent, and it's also timely so that the already good established in the past doesn't break off, and then we can continue the collaborations and move forward together. I also take note that there are still existing negotiations for the MOU. I think both sides are now looking into the details of this, but from our sides, there are specificalities and there are needs from Indonesia that needs to be adjusted so that we can fulfill the MOUs on our sides. I know that the ball is in our court, but let me assure you that these are being discussed and being packaged by Indonesia, and in due time we will give a positive response on this. Bapak dan Ibu sekalian, ladies and gentlemen, I wish today's meeting a great success. I hope that the exchanges not only will make us closer, but will bring us more into fruitful endeavors in the future. Thank you so much. Good morning.
Thank you so much, Mr. Dino Kusnadi. Ladies and gentlemen, now we would like to invite the Deputy for Nuclear Energy Technology Batam, Mr. Suryantoro, to open the webinar. Give you the floor, sir.
Thank you for Nina Widiawati, the master of this webinar ceremony. Good morning, everybody. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
To Mr. Dino Kusnadi, the Vice Ambassador of Indonesia in Beijing, selamat pagi, assalamualaikum. And to Mr. Xi Jianji, the President of China Zhongchuan Engineering Corporation, and also Mr. Ding Jian, Vice President of CEC, and all Batam colleagues, and also the participants of the webinar. First of all, I would like to thank to Mr. Dino Kusnadi on this morning speak that give support to our activities today, and also support to the collaboration between the CNNC and Batam, because as Mr. Xi Jianji mentioned that we have a long collaboration between CNNC and Batam regarding the peaceful usage of the nuclear energy. Yeah, and so I would like to thank to CNNC and also to CGEZ for this today occasion of the webinar, because we know that the webinar is a very important regarding the pandemic of the COVID-19, so we can have the webinar during online system. That I think it's a very effective and efficient, because it's a very difficult to have the offline webinar in Indonesia and also in the world because of this pandemic. So we have to consider about the health. Okay, I would like to explain about this Batam activities. You know, Batam is the research and development institution in Indonesia. We have a responsibility for the implementation, for the research, and also the development to implement the nuclear energy in the various fields, such as in the health, agriculture, environments, and also some of activities regarding the using of the nuclear energy. For the health, yeah, we know that the application of the nuclear energy is a very extensive in Indonesia, and also for the agriculture, we can produce many very high quality of the crops like the rice and also soybean and others, and also for the environment. So we have some activities on that. But for the energy, for the power, when the nuclear powers, we still have still a discussion. We have not implemented yet, but because of the policy of the governments that we have to increase our EBT, that's called the new and renewable energy. So we have to reduce the carbon because of the green effect gas that will have the change the climate. So we have to stop to reduce the carbon emission from the fossil sources. So it's mean that the new and renewable energy will be implemented in the future, especially the nuclear energy. Nuclear energy, we know that can support the very stable, the high power, and also it can change the what we call this is the coal energy that have a big emission of the carbon. So today's seminars is very important, I think, because they will have information from the China side, because we know that China is a very, what we call, is a very, what we call is an aggressive on the development of the nuclear power. We know in the world, China is have a development of the NPP, the construction of the NPP, and also we know that they also have so many construction there. So not only in the implementation of the energy, so China has a good research and development in the new power with the new technologies, that the generation 4. The generation 4 is will be a very promising, because it will be more safe, and also we hope it will be more economic and will be reduce the waste, because the problem of the NPP is the cost, waste, and also the safety. So with the innovative of the technology of the NPP, it will be very good for Indonesia to implement the nuclear power using the new technology that is safe, the cost competitive, and also the very low waste. We hope the NPP, nuclear power, and technology will be implemented in Indonesia. Okay, I don't want to talk too long about the nuclear power. I would like to officially open the international webinar of the nuclear power and technology collaboration between the CNNC and Batam. By saying Bismillahirrahmanirrahim, I open this webinar. Thank you very much. Hope we have a fruitful discussion of the webinar and we have a good beneficial of this webinar. Thank you very much.
Thank you very much, Mr. Suryantoro, for opening the webinar officially. And now, ladies and gentlemen, we would like to invite Dr. Suparman as Head of Center for Assessment of Nuclear Energy System, Batan, to deliver his presentation about the latest development of nuclear energy in Indonesia. Mr. Suparman, the stage is yours.
Thank you, Ms. Nina, for the time given to me to make presentation regarding the nuclear energy development in Indonesia. First of all, I would like to say thank you for the time given to me to have a chance to share with you the development of nuclear energy in Indonesia. Please allow me to share my presentation. Sorry, could you see my presentation?
Yes, Mr. Suparman.
Okay, thank you. Honorable Mr. President of CEC, Vice Ambassador of Republic of Indonesia in China, Pak Dino, Mr. Suryantoro, and ladies and gentlemen, good morning, selamat pagi, assalamualaikum warahmatullahi wabarakatuh. Allow me to give you current status of nuclear energy development in Indonesia. As introduction, based on our nuclear law, that there are two types of power reactor in Indonesia, namely non-commercial and commercial. Non-commercial means that the build and operate of this type of nuclear reactor is just for research purposes. And the implementing organization in this regard is the BRIN or Batan, because now Batan is under BRIN. BRIN is a national agency for research and innovation. And for the commercial power reactor, for policy level is Ministry of Energy and Mineral Resources, and the implementing organization or institution is become a state-owned company or private company or cooperative. This based on the nuclear law in Indonesia. And now we know that the nuclear law in Indonesia being revised, under revision, and we don't know the future because maybe the nuclear law become more how to say to make more and more easy to implement nuclear energy in Indonesia. And these activities on nuclear power program in Indonesia, as I mentioned before, that there are two types of activities that regarding non-commercial and commercial power reactor. For the non-commercial, Batan have activities since 2014 until 2015. We conduct site evaluation for experiment power reactor in Serpong area, or we call RDE project. And we got a license, site license in 2017 from the regulatory body of Bapeten. In parallel, we developed conceptual design with the consultant from Renuco. Renuco is a consortium from national and international company. Nukem from the Germany, and Renuco is a Rekayasa, Nukem, and Kogas. These three company become one company, joint company, to develop the conceptual design of experimental power reactor. In this project finished in 2015, and then Batan team, this not Batan only, but this national team. We also have other participants from for example, from the architect design from private company, and then we develop the basic design. Continuing from the conceptual design from Renuco, and then we make our develop a basic design of experimental reactor. This project finished in 2018, but unfortunately the program was suspended by the government. The project admin that, but we still continue the program of basic design by Batan Israel. One reason why the government was suspend this program, because the government think that the program or the project is too expensive, and then the capacity of power reactor is very low, only 3 megawatt electric. So the government want to build the commercial one and with the capacity until 100 megawatt. It's all small modular reactors. So that way the Batan was appointed by government to conduct the feasibility study of SMR in West Kalimantan Barat under National Priority Program. The duration of this program is until 2025. We start in 2020. And for commercial power reactor, we know that we have finished with Bangka feasibility study in 2013. And then after this, the Ministry of Energy developed the white book of NPP, this 5,000 megawatt. But until now, this book not yet published. And then Ministry of Energy also developed NPP roadmap, but until now the roadmap doesn't finish yet. So now I would like to explain more detail about the National Priority Program, because this is the current status of our energy, nuclear energy development in Indonesia. The National Research Priority on NPP is based on the Ministry of Research and Technology Regulation number 38, 2009. This target of this research is nuclear power generation technology for commercial use with a variety of consideration and the technical document. As coordinator, Batan was appointed this program, and the candidate site is in West Kalimantan Barat. And we focus on the technology of SMR based on the light water reactor. It could be PWR or PWR in this program. But in the next program, I think another type of technology of NPP can be participated. For example, for the high temperature reactor or for the molten salt reactor. This activity of this in this research priority, there are three main activities. The first one is a feasibility study. In this feasibility study, we conduct technology choice, economic and funding analysis, and also electric system analysis, site study, and etc. And the second activities in this priority research, national priority research, is mastery of NPP technology. We study on the nuclear fuel, how to boil, how to develop the nuclear fuel, in waste management, in material technology, and non-nuclear island. And the third activities, this also the important activities. In supporting activities, we conduct the socialization in West Kalimantan Barat, and also a stakeholder engagement, regulation, human resource development program. In this research priority, we have a collaboration scheme, not only Batan, but many institutions, universities, and also the local government involved in these activities. For example, for the site evaluation, Batan have cooperation with the Bapeten, also from the Ministry of Mineral and Energy and Mineral Resources, and also from the PMKG. PMKG is for the meteorology. And for the feasibility study for non-site, we have cooperation with the Ministry of Energy and also the Indonesia Power. Indonesia Power is one of the company under PLN that interesting in the activities. And also some universities involved in these activities. For example, from the Gadjah Mada University from the Yogyakarta, Institute of Bandung in Technology, and also the local universities, Untan. Untan is Universitas Tanjung Pura or Tanjung Pura University in West Kalimantan Barat. Now the status of national research priority. As we know that from the IAEA, we have a guideline how to perform the nuclear energy program in Indonesia. Based on this infrastructure development, there are 19 infrastructure issues should be prepared before we implement the nuclear energy. And we have in your mission in Indonesia as integrated nuclear infrastructure review that the IAEA have a review our readiness of infrastructure, and then they found that there are still 3 issues that not ready yet, namely national position. We know that until now the government not yet make decision to go nuclear. And then follow it, we know that until now there is no NEPIO in Indonesia. In the management aspect, there is no operator candidate decided. And then in the stakeholder driven, we need to be improved. So regarding this national issue, 19 infrastructure issue, we developed the research priority under IAEA milestone that we know that in the phase one is pre-project activities. We have should conduct feasibility study or pre-feasibility study, and also we have a survey site of site, and these 2 activities to strengthen the national position. And we hope that from these activities, the government will make a decision. This is milestone 1. This decision is very important to continue to the phase 2. This is the project activities. And then this roadmap, as I mentioned before, but that we still in phase 1, this pre-project activities. We hope that into 2024, this project will finish, and then this activities, pre-project activities, will be consideration for government to make decision. The president, we hope that will make statement to go nuclear, and there will be NEPIO, and the nuclear energy will include in business plan of utility company. Our RPTL, this business plan of utility company or PLN. And then after this, we hope that the state-owned company, private company, or cooperative will continue to construct nuclear power or SMR in this in West Kalimantan Barat. So Batam only involved in the pre-project activities because this commercial nuclear power plant. So Batam not allowed to construct nuclear power plant for commercial purposes. So we only prepare the pre-project, and then after this, the pre-project study, including site evaluation as consideration for the government to make decision. What we have done in 2020, that we have conduct study, and as I mentioned before, that there are many institutions involved in these activities. For example, Ministry of Energy and Mineral Resources Research and Development Center. They have conducted the energy and electricity analysis, economic and financing, and also cost benefit analysis. And for the University of Gadjah Mada in Yogyakarta, they have done the business process, economic impact analysis, and also management aspect. And our partner from the BPPT is a technology assessment and implementing agency. They carry out the national participation for non-nuclear island. So how many percent our national industry will participate in this project? And Batam accept we carry out the technology assessment, technology choice, and also we conduct national participation for nuclear island. These activities in 2020. And for the site study in 2020, we have many aspects have been done in this year. For example, for the demography, geology, hydrology, meteorology, and so on. And we still continue in this year because we need time for example, for the geology survey. We need time also need for money to conduct this aspect. So why we select West Kalimantan as candidate site? Because we know that in West Kalimantan, lack of electricity, they still import electricity from Malaysia, Sarawak, Malaysia. So that's why the government of Kalimantan Barat asked to the president to build nuclear power in West Kalimantan to fulfill the demand in West Kalimantan Barat. And another consideration why we choose West Kalimantan Barat, because in West Kalimantan Barat there are many potential demand from the industry. The government of Kalimantan Barat now was developing the international port in near the candidate site, this Kijing international port, and then the West Kalimantan Barat government want to build the integrated industrial park near this port and aluminium refinery. So the demand is quite big in West Kalimantan Barat to support this industry. Right now, the share of demand of electricity in Kalimantan Barat still dominated by household, around 62%, and industry still low, is very low, 7%. So that's why we need to make industrialization in West Kalimantan Barat to enhance the socialization in West Kalimantan, economic and socialization in West Kalimantan Barat. Another information we choose West Kalimantan Barat because, as I mentioned before, that West Kalimantan Barat still import electricity from Sarawak, Malaysia, around 230 megawatt, almost 50% the peak load from in the West Kalimantan Barat. So this very curious because some body in West Kalimantan Barat thinking that if the Sarawak or West Malaysia stop the electricity to West Kalimantan Barat is quite very dangerous for the electricity supply in West Kalimantan Barat. So that's why the many people agree with nuclear power plant development in West Kalimantan Barat. The other thing that diesel in West Kalimantan Barat still high, more than 100 megawatt. Another thing that we know that the government of Indonesia want to move the capital city Jakarta to East Kalimantan Barat, and then the PLN have a plan to make a transmission line from the West Kalimantan Barat to East Kalimantan Barat. So I think if the capital of Jakarta move to East Kalimantan Barat, and then there are many demand in East Kalimantan Barat. So from the earthquake, West Kalimantan Barat is very stable because there are rare earthquake happen in West Kalimantan Barat only 4 or 5 times in West Kalimantan Barat. And then from the volcano, there are no volcano active in West Kalimantan Barat. This our candidate site located in Gosong Beach, West Kalimantan Barat, the northern of Pontianak. Pontianak is the capital of West Kalimantan Barat. In front of the Gosong Beach, there is Samosir Island, and the distance between beach and the Samosir Island is around 1 kilometer. And for the potential site, we have another site, not only for the in West Kalimantan Barat, we have also another site, for example, in Lemuria and Bangka and also Banten. West Kalimantan Barat is Kalimantan Barat. For the large scale of NPP can be developed in Sumatra or Java Island because the transmission line or the demand is quite big to have a large scale of NPP, but for the SMR, for small modular reactor, can be developed in eastern part of Indonesia, for example, in West Kalimantan Barat or East Kalimantan Barat, and also in part of eastern of Indonesia. I think that's all my presentation. Thank you very much for your kind attention.
Thank you very much for the excellent presentation, Mr. Suparman from Batam. Ladies and gentlemen, now we will begin the main session of our webinar today. And the speaker for this session is Mr. Sun Jun from Tsinghua University with the topic 1, the latest development of HDGR. Mr. Chen Bin from Synergy with the topic 2, ACP100 by CNNC in China, and Mr. Jiang Huixia from China Nuclear Power Engineering Corp with the topic 3, HBR 1000 reactor of CNNC. And this session will be moderated by Mr. Huang Yuliang from CGEC. Give you the floor, the moderator. Thank you.
Okay, thank you. Thank you, Dr. Superman, for your very comprehensive presentation on the latest development of nuclear energy in Indonesia. And now I would like to introduce Mr. Sun Jun, Associate Professor and the Division Head of Reactor Physics, Thermohydraulics, and System Simulation from Tsinghua University. He is very experienced in HTGR development from the very beginning of the introduction of the technology to China. So he will give us a presentation on the latest development of HTGR on China. Mr. Sun, please.
Thank you, Chairman. Thank you for the introduction. Actually, I'm very honored to join this event and share development of HTGR in China. And also, I'm very glad to have those speeches from the excellencies and the dear friends and all the lovely faces from Indonesia. Yes, today I want to share what happened recently in China about the development of HTGR technology. So again, my name is Sun Jun from Ainan Tsinghua University. As the agenda says, my outlines will cover those topics, including the short introduction of HTGR in the world, some important points I want to emphasize, like technical features and some safety concept. And important ones are the roadmap for development of HTGR in China, including test reactors, demonstration plans, and also commercial ones. And the last, I want to introduce a little more about nuclear safety regulatory framework in China. So as we may know that the generations of reactors have been divided into more than 4 in the world, including many kinds of reactor technologies. At the very beginning, we also have prototypes of different reactor technologies. At that time, if you can mention here the red line, that we also have gas-cooled reactors. And here in the 21st century, in the Generation 4 International Forum, we also have the VHTR as one of the candidates for the future plans. So we all know that the gas-cooled reactor has the same history as the other kind of reactors. So at the very beginning, we also have early types gas-cooled reactors, but at that time we use carbon dioxide as the coolants, and we have more than 50 units built in the Europe, in the Great Britain, and the other countries. So after that, we realized that we want to increase the temperature output of that reactor. We change the fuels into ceramic coated fuels. We change the coolants to helium so that we can increase the output temperature up to 700 degrees C or even higher to 950 degrees C. At that time, we have 3 test reactors built in the world and another 2 prototypes in both Germany and the US. So after those experienced in the early in the HTGR reactors, we found that the safety issue must be emphasized for all this kind of reactors. Then we have the idea of inherent safety and the concept of modular HTGR. By this kind of concept, we can realize the self-acting decay heat removal of this design, and we have followed this concept to build test reactors and several designs. So this slide have showed several past HTGR built worldwide. We can see clearly from the table that we have test reactors, demonstration plants, and also the 2 test reactors from Japan and China following the concept of modular HTGR. So about modular HTGR, what's the technical basis for that? So most importantly, I think there are 3 important points I want to emphasize here. First one, we use helium as the coolant because it has very good chemical and neutronic features. The second one, we use a lot of graphite as the moderator and the structural materials. And also the most important one, we use the unique design of tricycle particle as one of the few. So by these major features of the modular HTGR, we can realize very high temperature operation, and more than the electricity generation, we have more non-electric applications. So under the framework of a GIF Generation 4 International Forum, we have built a technology roadmap for this kind of technology. At the very beginning, at the year of 2002, we want to realize the higher temperature output as high as 100 degrees C, especially for the hydrogen production market. And after 10 years of experience, we found that we still have a larger market for the temperature range between 700 and 950 degrees C. So we divided the technological roadmap into 2 phases. So right now we still have more efforts to realize the temperature around 750 degrees C. So if we want to simply compare HTGR with PWR, we can distinguish between those 2 technology and find the technical differences between these 2 reactors. Clearly from the table, we can find that we have different coolant, different output temperature, different structural materials, and the fuel material. And most importantly, we found that the power density is quite different. For modular HTGR, the power density is almost 1/30 of that about PWRs. And that feature will ensure one of the important concept about inherent safety. So one of the important features, as I said, is the cooling media. So helium is a very favorite one because it's chemically inert, means that it has no reaction with other materials, even for high temperature operations. It's single phase, it can resist the high temperature. And also among those gases used as the coolants, helium has very high heat capacity. And also for the neutronic part, The helium is almost transparent to neutrons, means that it has a very low neutron capture and also zero moderating capacity. And also for helium, it's very easy to be purified during the operation. But still for helium, we have some challenges. For example, the helium has very small molecular mass. That means that it's easily to be diffused during operation. Because of the leakage, we have to face the sealing techniques. We have this supplement system during the operation. Of course, for helium, it's have very low density, means that during the operation, we must pressurize this helium for the operation. And also we have the risks of losing the coolant during the operation. For graphite, it was used as the structural material and also the moderator and also the reflector for the design of HTGR. Graphite also can resist a very high temperature. It has very high thermal conductivity and also high specific capacity. Those features will give good basis for the high temperature operation. So as the operator, the graphite will summarize the fast neutrons, means that the HTGR is had a thermal spectra. And for the graphite, we still have challenges. For example, it's not easy to purify this graphite during the fabrication, and also during the long time irradiation of the dimension will change, and also the properties of the graphite will change in terms of thermal conductivity and the elastic modulus. And also during the operation, we still have risks for the corrosion of the graphite if we have the water ingress or air ingress accident. Another important feature of HTGR is that we use the triso particle and as various types of field element. The triso particle means that we use more than three layers of structure as just very small particles. So if you can follow my mouse in this slide, in the middle is a picture of the triso particle. In the middle of that is the kernel, and outside we have several layers by the pyro carbon coatings. And one of the important layer is the silicon carbide that will have the function to retain the fission product inside this triso particle during the normal operation and even extended scenarios. So by this very small size of the triso particle, we can apply and then we can use this distribute these particles into graphite, or we can use the spherical element to for these particles, or we can put that into the compacts. So by the spherical element, we can design the pebble bar type HTGR, or by the compact of these few elements, we can have the shape of a block type element and also the design of prismatical HTGR. So following the modular HTGR designs, we can have a prismatic designs or pebble bed model designs. As for the prismatical designs, the very pioneer one is the MHTGR from the US. And after that, we have other kind of designs such as GTMHR from the joint design of Russia and the US, HTGR from Ariba, and also HTGR from Japan. And following the design of pebble bed modular HTGR, we have the early one as HTGR module from Germany. And also following that, we have PBMM from South Africa, HTR10 from China, and HTRPM from China. So the important one, as I mentioned, is that the modular HTGR follow the idea of inherent safety. Inherent safety also have other names like intrinsic safety, meltdown free reactor, or catastrophe free or walkaway safety, and etc. So those concepts or names of this one means that following the inherent safety, we can have those fundamental measures to ensure the safety without any additional systems. So from these three aspects, like control of the power, removal of the decay heat, and also the retention of the radioactive materials, we can realize the inherent safety design, and we can keep it safe after accidents. So I will introduce them one by one. The first aspect is the reactivity control. We know that this is important for the design of a reactor. For HTGR, we can realize the full range negative feedback, and also the most important one, we have larger margin for temperature increase during the accident. If we compare a little about this kind of design with PWRs, we can utilize almost a 100-degree temperature increase during the accident. But for PWRs, maybe we can only use like 20 degrees C. So even we have the same level of negative temperature feedback, but when it multiplied by this different temperature range, we can have the different reactivity compensation during accident. So clearly for a modular HTR design, we can have a very large negative reactivity compensation during accident to ensure the safety shutdown in any conditions. So this kind of reactivity control measures have been demonstrated and approved by HTR in China. Around the year 2004 and 2006, we have several safety demonstration tests, and that was witnessed by many international experts from the world. So these pictures show that by this very severe accident of this kind of design, we can realize the safety shutdown of the reactor. The second important one is the decay heat removal. We all know that after the fission process, we will get the decay heat during the very long processes. But for this process, we have to use even the additional systems or some design of the system to remove that after the shutdown. So in the history, we have many ways to achieve that. For example, we can use active system to do that, or we can apply passive system to realize the decay heat removal. But for modular HTGR, we have very different idea. We use the word self-acting removal because, as I mentioned, for this design, we have a lot of material have higher specific heat or higher thermal conductivity. So during the higher temperature operations, we can use the natural properties of this material to remove the decay heat by heat conduction, heat radiation of those materials. So for the design HTGR, we have those support from the nature properties of a material, and we can realize the self-acting heat removal itself. So if you can see the left bottom figure of this one, we can find that because we have the very lower density of the HTGR, and by the thermal conductivity and also the specific heat of those materials, the HTR can increase the maximum temperature in a very long time. And finally, the peak temperature will not exceed the field temperature limit. So by any accident, without any electricity input or other additional systems, the HTGR can be safe in terms of decay heat removal. The last one is about the radioactive retention, meaning from the design of the triazole particles. So as we all know that we have the idea of in-depth multiple barriers to retain the fission product inside. So we also have the idea, but we emphasize the first barrier as the silicon carbide coating. So for the silicon carbide, it can resist as high as 1600 degrees C in a very long time. So during the accident, if the fuel temperature will not exceed that temperature limit, the silicon carbide will ensure the retention of the fission product inside this billions of Pressel particles. So this feature should also be approved or validated for radiation tests. We have fabricated those samples from our university. We send those samples to Patton, Netherlands for iteration test, and also we send those samples to Germany for post-irradiation examination. And we found that both for normal operation or accident temperature scopes, we have reached a very good result, which means that the design is also validated. So we can find more information and knowledge from the recent published book by Professor Pugler and Professor Zoe Zhang. You can find that from the English version from Spring. So about China, actually, as I mentioned, we choose the pebble bat HDGR, and we still have very clear positions in terms of HDGR technology in China, especially from the power generation, cogeneration, and also the hydrogen production part. In China, we have begun our research from the 1970s. It's almost about 50 years. After we know how to design the reactor, we try to build our own test reactor HTR10. And then we right now are undergoing the demonstration plant called HTRPM. And after that, we continue with our commercial plant designs and applications. So for HTR10, it was strongly supported by the central government. We have the National High-Tech Program to support the design and the construction. And we begin our construction by the year 1995. After 5 years, we reached the first criticality. And after that, we have 3 years operation for the full power. And after that, we have demonstrated many kinds of experiment to prove and understand this kind of design. So in recent years, we still restarted the HDR10 and operated for many purposes. One is to train the operators of HTRPM. Another purpose is for further experiments. For example, to measure the temperature inside the pebble bat core. And in this year, we still have another program to support the very high temperature operation. So you can find some of the major design parameters about HTR10. I think many Baton colleagues have visited our facility in Beijing. For HTR10, we have many operation modes, such as like electricity generation, cogeneration, or only the heat production. The safety demonstration tests are also famous because they proved the design of modular HDGR. So by HDR10, we have many achievements, especially for the experience and the capacity building of the humans. We understand how to fabricate the fuel, and we also have a lot of discussion for the safety demonstration and license with the NNSA. So HDR10 is a good base for us, and also an essential base for us to continue with the industrial or commercial development. So after HDR10, we have the idea to have a larger scale of HDGR called HTRPM. The Chinese government continue to support us from the R&D part, and we have a very good team to deliver this technology for the industrial application. So from these slides, we know that we have a good team like INET, Chinergy, Huanan Group and also CNNC, we got a very good suppliers from many domestic China. So the location of the HTRPM site is in Shidao Bay, Rongcheng City, is in the eastern part of China. From this feature, you can know the general design of HTRPM from different buildings. So in the middle, we have the reactor building. We have 2 reactor modulars, which can generate a very high temperature steam to 1 steam turbine. And we also put the spent fuel storage close to the reactor building. We have the auxiliary building here, which include, for example, the helium supplement system or helium purification system. We have the main control room located in the control building. For each NSSS modular or reactor modular, we have the design like this. It's a side-by-side design of the reactor pressure vessel, steam generation vessel, and we also have a heat conduct vessel to connect these 2 And for each reactor, it can generate about 250 megawatt thermal. And because we have a smaller power density, the core size is large. So inside this reactor, we have around 420 fuel pebbles inside, and by these pebbles, it can hit the helium up to 750 degrees C. So about these 2 NSSS, the heat will be transferred from the reactor core to the secondary side of steam generator. These 2 steam generator will combine the steam into the steam turbine to generate electricity. And also by several levels of steam extraction, those steams can be used to heat up the feed water and also to increase the energy conversion ratio of this whole plant, which could be around 42%. So this kind of design are the important basis for modular HTGR if we want to enlarge the power output in the near future. So by HTRPM, of course, it followed the design of a modular HTGR, but the implementation of engineering and technology is quite unique in China. For example, we listed several important items about the innovations and also published that in a recent paper. We use more than 1 reactor modulars. We have a design of helical coil tube bundles for the steam generator. We use electromagnetic bearings for the shaft of the helium circulator. We use a different combination of reactivity control system. We improve our fuel handling system designs, and also we use the dry storage system for the spent fuel storage. So if you can see that the scale of these designs are new, so we have to verify those designs by the full scale and the full environment under the helium conditions. So we have our own engineering lab for all these tests, and we finish all those tests and prove the design can meet the requirement from the regulatory. And as I mentioned, just when we finish the full power operation of HDR10, we have the idea to design HDRPM. From 2004, we started the standard design. Then we get support from the government and also the industry partners. Then we continue with our preliminary design, the safety and assessment, and also those verification processes. And after 2015, we almost finished the civil work of Nuclear Island, and then we started the installation of important components such as the reactor pressure vessel, the metallic internals, the water cooling panels of RCCS, and also other important systems like DCS and the full scope simulators. And between the year 2017 and 2019, we continue with the installations. Most important and most complicated one is the ceramic internal structures. If you can see from this picture, in the structural material are thousands of blocks of graphites and carbons. So it's important to put every blocks into the position and put the shape together. And also we have the installation of a steam generator and a helium circulator during that time. And then when we come to the year 2020, we started our commissioning. First, we have the cold test that the pressure boundary will reach the design limit. And also after that, we are started the helium circulator to heat it up to 250 degrees C. And in this year, and in March of this year, we finished the hot test of both reactor modulars. At the same time, we have fabricated enough pebbles to prepare for the fuel loading. We have delivered the first batch of fuel pebbles to the site at the beginning of this year. And in just this month, last week, we almost finished the steam turbine test, but the non-nuclear steam. So everything is ready for the fuel loading. I think we may have the exciting news in the coming months. So after HTRPM, we still have plans for the larger size and a commercialized HTGR. But based on HTRPM, we have something to use as the same or proven technologies, such as the design of the NSSS modular. We will use the experience based on those engineering tasks, those design, manufacture, construction, commissioning, licensing, and even the project management. Those experience accumulated during the last 10 years, we are shorten the time. Also, will decrease the cost of this larger scale HTGR. We have 6 or more NSSS modulars for the near future designs. Right now, we have finished the standard design of HTRPM 600, which includes 6 reactor modules inside the nuclear power plant. And also, we continue with the feasibility of some candidates' domestic size of that. The important thing for the design is to further lower the cost and try to have some economic competitiveness with other PWR designs. So as the last part of several points about the nuclear safety regulatory framework in China, actually China had developed its new nuclear regulations based on IAEA frameworks, but it also combines with the national conditions and the experience during the many years of practices. So actually we have the same framework that for IAEA, and also during the licensing processes, the technical goals, safety requirements, the masters are consistent with the international safety standards. Also, during the safety review and the licensing of HTRPM, it also generally follow the China's NNSA nuclear safety regulations and the gas. And for the licensing processes, the NNSA can issue those permit or licenses, such as a siting, construction permit, operation license, or permit of decommissioning, and the license for operators. And those are important for the design and operation of these nuclear power plants. So that is almost all my points try to deliver in this presentation. And before I end my presentation, I want to emphasize or mention that between the Indonesia and China, where we have very good and a solid foundation in the field of collaboration, especially for HTGR. We have a joint lab on HTGR, which was funded by both ministries of two countries. So under the new framework of Belt and Road Initiative, I think we can continue with the collaboration in terms of education and the training on HTGR. So thank you all for listening. Thank you.
Thank you, Dr. Sun Jun, for the presentations. Very good presentation, very clear, I think, for this morning. Ladies and gentlemen, we have a few questions here for Dr. Sun Jun and Dr. Suparman as well. Hopefully, Dr. Suparman is still here. Dr. Suparman, yep. The first for you, Dr. Sun Jun.
Yeah, okay.
From Mr. Sriono. Dear Dr. Sun Jun, may we know how far the China HTGR cogeneration research for hydrogen production been? What the methods are used for the hydrogen production as well? Is there any using a kind of IS or like in Japan here, like HTTR, for example?
Yes, thank you for the question. Yes, so actually I didn't mention too much about the hydrogen production or very high operation of HTGR, because those things are still under the framework of R&D, which also get fully supported by the central government. So actually, for the hydrogen production part, we prefer to use the chemical solutions like IS processes. We have the test facilities in INET to do this research, and it's important that we can enlarge the capacity to be produced in the near future. And also another important one, as I mentioned, for HDR10, we have the idea to increase the temperature output up to 850 degrees C before 2025. So we have the program supported by the central government. Right now we have the design how we can reach that high temperature is under design, and also we have the plans to discuss with the NNSA about how we can operate HTR10. So right now the R&D are actually separately by the reactor side and also the hydrogen production facility side, but I think after we prove that, we have the plans to combine these two facilities together for the later tests. So I think that is my answer for your question, Mr.
Okay, great.
Yeah. Thank you.
That's from Mr. Sriono, actually.
Yes, thank you. Okay. Thank you, Dr.
Okay, okay, sorry. Yeah.
Thank you, Pak Sriono. Hopefully it's answer your questions. Okay, the second one from Mr. Suryantoro, from Mr. Deputy here. Okay. Question here about the spent nuclear fuel from HTRPM. What is the strategy? Is there any processing or direct disposal, for example, here?
Okay. Thank you for your question. It's a very good one. So actually, as you can see, for the design of HTRPM, we put all the we have the capacity and also the enough volume to put all. I mean, the lifelong time spent fuel to put close to HTRPM in the storage, spent fuel storage. That is planned for HTRPM. And also after that, we have the strategy for reprocessing. We also have the R&D project for how we can do that and lower the cost of the reprocessing. Yeah, that is our plans for that. But still, HTRPM is the very first one. So still, it means that we have longer time to finish the R&D part.
Great.
Thank you.
Great. Thank you. Okay, we come to the third one here from Mr. Tukiran. about the code test of the HTRPM. What did when you did the code test experiment for the HTRPM? When you planned it about that, and what kind of the experiments did you do, and how long it takes for the experiment? Could you tell us a little bit about the results as well?
Yeah. So thank you for the question. A code test, I think, is the very first step for the test of the reactor. As I mentioned in the slides, it was finished last year. We have to do the code test for both reactor motors, so it has been finished twice. For each one, the most important one is that we have to increase the temperature, the pressure of the reactor. Means that we want to test whether the pressure vessel can resist those high pressure limit of the design. And also we want to get whether there was some leakage from the boundary conditions, from the boundary vessels. So that is the important objective of this test. I don't remember how much time we spend for each test, but normally for the pressure limit, we will put the limit into several stages. We will increase the pressure step by step. And when we reach the pressure limit, then we will decrease the pressure down again by several stages. So that is the normal standard how we can do the code test. The important thing is the pressure and the release.
Okay, great. Thank you so much, Dr. Sun Jun. Hopefully it answer Pak Tukiran, yeah. Wow, you got a lot of questions here, Dr. Sun Jun. Okay, the next one I will write it about the safety here. I think it's quite interesting here from Mr. Baskara Putranto. It's right out in Indonesia actually, but I'll try to translate it for you. Okay. How about the possibility of Chernobyl and Fukushima incident here for HTRPM in terms of safety? Are there any special design or special safety feature, for example, to avoid that kind of Chernobyl or Fukushima accident?
Okay, yeah. I think as I mentioned in the slides, I talk about the safety issues called inherent safety. So if you can stand the basic countermeasures for those some called severe accident, the inherent safety of modular HTGR was ensured by the designs. So typically it's from the combination of materials. So as I mentioned, there are three basic aspects. First one is, we can shut it down. The second, we can remove the decay heat by itself by the thermal conductivities of those materials in the reactor core. The third one is that we use unique triazole particles to retain the efficient product during the normal operation accident scenarios. So these three basic features can ensure that the Fukushima accident will not happen for HTGR, for modular HTGR. So yeah, if you have interest on that, we can have further communication. Yeah, thank you.
Okay, great, thank you. So basically, HTGR technology is safer than the Fukushima type of nuclear power plants. The next one is from Mr. Ari Batan here.
Yeah.
Dr. Sun Jun, why China prefer to use pebble bed instead of prismatic fuel? Is it related to the safety aspect or there's any other reason? And the second one is, since it is taken more than 30 years from research into the commercial HTGR, how do you think about the first HTGR in Indonesia? In the near future, should we have to follow from scratch like China? Yeah, like China has been done here. Is that very hard to catch up, or do you have any suggestion about this? Thank you.
Yeah.
Thank you, Pari, for the question.
Yeah, thank you, Ari, for those two good questions. The first one, I think it's not from technical side. I think it's historical side. So I think for both prismatic and pebble bed, they both follow the design idea of modular HTGR. So both kind of design have the inherent safety. So I don't think it's have the safety aspect differences. So I think the most important thing is historical reasons. But I was not born at that time, so I don't know too much details. yeah, this is the first one. The second one, I think, it's important. Actually, I also happy to know that Indonesia have a lot of people and a lot of experts involved in this HTGR development. And then in the last 5 years, we have a lot of discussion under the framework of joint laboratory. So I don't know, from my personal idea, I think we have to realize our goal, realize our dream step by step. So firstly, importantly, as I mentioned, we can continue with the education and the training aspect. Then we have can enhance our communication by the like staff exchange, technical exchange, or even more training workshops. So we can now understand how to design and how to understand the safety features of this reactor. Then after that, if it is supported by the government and the other companies, I don't know, maybe you can maybe build a test reactor, then we can continue with the further collaborations in many fields. So yeah, from my personal idea, because I'm from a university, so we can start by the capacity building.
Yep.
Thank you.
Okay, great. Thank you, Dr. Sunjun. We can start with capacity building, I think.
Yeah.
And okay, we've got another question here from another two question, I think, for you. Before the time is enough for you. First time, another one here from Mr. Sumiran. In China, there are more than 50 nuclear power plants. He said that. What about the other nuclear power plant, other power plant? Here, he said that about the coal-fired power plant here as the example. Are they still used, or how do the other compare now? Yeah.
So China, we still have a lot of coal-fired plants. So as the basic load for the electricity generation. So even we have 50 units of nuclear power plants, I think it's only contribute to around 4 or 5% for the electricity generation. Still, we have a long way to go if we want to face the challenge from the climate change. But still, as we all know that the nuclear power plants as one of the, if we may call clean energy or new energy, because it has free of the carbon dioxide emission. So it has an important role if we want to realize the carbon neutral object in the near future. So it's important how we can face this challenge, how we can promote our nuclear technology in the near future. So in terms of application of HTGR plant, we have plans to replace or repowering some of the retired coal-fired plants, because we can use the same site or even the same steam turbine in the retiring coal-fired plants and replace the boilers by our reactor modular of HTGR. So that is maybe a very promising way to face the climate change situation and also apply this very safe HTGR technology in China. And that is also under research. Yeah,
okay,
that
great.
is our plan.
Yeah, thank you. Another question from Pak Rohmadi here. Is there a probability of corrosions in the steam generator structure? Here is asked about this corrosion of the steam generator. How to anticipate it early?
Yeah. I think it's also important for both technologies. So actually, the important thing is how we can control I'm not sure, the concentration of those impurities for the feed water. So I'm not a water chemistry expert. I don't know too much details about that, but normally we have those chemical system to ensure the quality of those feed water. Yeah. I think it's common for both reactor technologies. There is no big difference.
Okay, great, thank you. The last one here from Mr. Joko Birmano, Dr. Sun Jun.
Okay.
He said that I want to know the present status of HTRPM. Your presentation stated operated since 2014, but many literature stated not yet operated until now. Okay, I think it's Dr. Sun Jun already mentioned this in the presentation. That's fine. Probably you can explain again, Dr. Sun Jun.
Yeah, we are still waiting the permit to load the first field. So maybe you'll get the news soon. Yeah.
Okay. Thank you so much, Dr. Sun Jun. I think that's
Okay.
all the question for you. And ladies and gentlemen, I will try to hand over again the floor to Mr.
There is still one question from Pak Suryantoro, but the thorium in HTRPM is possible to use thorium?
Oh, really?
Yeah,
Okay.
Yeah,
Sorry,
actually,
Pak.
technically it's possible. We also know that we have THTR 300 in German, means that we can apply this kind of fuel into the operation of HTGR. That's possible. And also HTGR is very flexible by using different fuel cycles. So I think it's possible. But right now, we still have many problems like reprocessing related to the thorium, uranium cycles. So I think that is technical problems. But still, for China, we may focus on the uranium cycle. So if we want to apply new fuel, it must be a longer time and more effort to be put into the R&D. Thank you.
Thank you, Pak Suparman. Actually, Mr. Suparman, you have one question for you actually here from Pak Sucipta.
Yeah.
Are you okay to answer it? Okay. He said that the question is for you, based on your opinion on policy, how about the concept of site for the radioactive waste management facility and how the disposal of radioactive waste, it will be near or away from the NPP?
Okay, thank you, Pak Sucipta, for your question. Ideally, the waste management facility should be close to the NPP site, because we know that if we have a facility of waste management site in Serpong area, and then we have NPP in West Kalimantan Barat, we need to transfer the waste from the Kalimantan Barat to Serpong area. It means that we need the cost of transportation, and there will be a risk of transportation of the waste. So ideally, it should be close to the NPP site. But for the final disposal, I think there is a political problem, because until now we didn't yet decide to make where the final disposal should be located. So we need to survey the area, remote area, or the small island in the remote area to have a final disposal. Thank you.
Great, thank you so much, Pak Suparman, for your answer. Okay, I think it's enough for Dr. Suparman and Dr. Sun Jun as well. I will hand over the floor to Mr. Huang Yuliang for the moderator to start the second topic for this morning.
Okay, thank you, Dr. Xiaofu. Thank you for your commentary. Now, I would like to introduce Mr. Chen Bing to bring us the topic 2, the SMR ACT100 by CNC. So Mr. Chen is from Chengchi, but he used to work in Nuclear Power Institute of China, who designed and developed this ACT100 reactor technology. So Mr. Chen is very dynamic, and he has very rich experience in international cooperation. I'm sure he will bring us a very interesting presentation. So you have the floor, Mr. Chen, please.
Thank you, Mr. Fang, and thank you, Chairman. Could you hear me clearly and loudly?
It's clear, sir.
Perfect.
Yes.
Perfect. Thank you. And as well as the presentation is not available for you all to see.
Yes, we can see it. Clear.
Perfect. So thank you all. It's my honor to be here today to show you the progress as well as a brief introduction of what we called ACP100, an advanced small modular reactor that designed and constructed and will be operated by CNC in China. And this is the very first demonstration project all over the world. And I'm really proud to give you the introduction. Okay, but start with Selamat pagi. I hope I can still recall the Indonesian, because I've been here. I've been to Indonesia in 2016 with the collaboration between customers from the Bali Island on nuclear technology for the medical treatment. We have a really long history between MPIC, which is a subsidiary company of CNC, and Indonesia, with Batam, Bapitan, and other partners in Indonesia. So I'm also very happy to see some old friends today and some new ones. My presentation today will be divided into 4 parts. I will start with some of the features of SMR, and then I will come to the applications. Because if we want to use something, we want it to maximize its utilization, to have all its benefits. The first thing is how we could use it. The purpose, to have the purpose in the mind. And then I will give you the whole picture, started from the R&D of ACP100 to its design, to its technical features, and last but not least, the demonstration project, which is now under construction in Hainan province of China. And then I'll come to the summary, a short story, actually. So the features of SMR, there's a very official definition by IAEA. And I like it because the SMR is suitable for small electricity grid, district heating, process heating, supply, CO2, distillation, and etc. So this is what we usually have adjective, compared to the larger ones, we say the SMR is multifunctional. So it can be used for a lot of things. And this is exactly why we have so many designs of SMR, and we have so many plans for the deployment of them. But so far, only we are doing it in real. Only ACP100 is under construction. And there's also one document compiled by IAEA called the development of SMR all over the world. It's an annual report, and you can download it directly from the IAEA website. It's quite interesting references that you can look after our seminar. So why China is so interesting in small modular reactors? The first thing is that it can do things that larger power reactors like HPR 1000 cannot do. So SMR is featured in small scale, simpler design, and lower cost. So economically feasible. Also, it actually has higher safety, could
have the technical feasibility to be built or even among denser population. It can be modular constructed. Some can be even constructed in plant and be transported to the site. Construction period could be dramatically shortened. And this is another good news to its economy. Also, it could have much more actually flexible siting requirements. So you don't need to find a large rock. It can be just implemented. One of the applications is to replace the fissile plant as flexible as that. Then come to the applications, because it has these features, the small modular reactor. The applications is vast. The things to replace of the coal power plants, especially in the northern part of China, there are a lot of smaller coal, the fissile plants, which generating the electric power less than 200 megawatts. And the phasing out of these plants is a national strategy to reach the peak carbonization in 2030, and as well as carbon neutrality in 2060. It's not only environmentally friendly, but also a very essential transmission of the energy portfolio of China. And we do believe small modular reactor is one of practical, or maybe the only practical replacement of the fossil plants. So it's quite fitting for small and medium electricity grids. For isolated grids, like for islands, as well as for small cities. And I do believe, as for Indonesia, called by the islands, the nation of thousands of islands, the small modular reactor is quite fitting for these situations. Also, it can provide for the special requirement like mining in remote areas, for the high energy consumption plants, things like. The other one we called is for regional heat supply. This is also a large part for the reduction of carbon oxide emission. The industrial heat demand in China is now around 1 billion tons of steam. And this occupying 10% of the total emission of carbon. Well, as for the heating of communities, the northern parts, it usually lasts for 4 to 6 months per year. And it takes 15% total energy consumption. We also hope the small modular reactor could be one of the zero carbon oxide emission source for these two applications. The other one is what we call floating power plant. Actually, Russia is ahead of us, and it has already constructed, it's now operating the floating plant in the near the North Pole, near the coast of Russia. And we are just behind them. And ACP 100 is a proven feasible technology to just be transferred for a floating power plant. The other one is what we call sea-water desalination. Coastal cities around our coastline, especially for the major cities in China, they are actually lack of fresh water. I guess some of participants today might have heard significant engineering project, what we call the transferring of the water resources from the west part of China to the east part of China. It takes nearly 20 years, and now it's under operation. But SMR is an alternative way to also tackle this problem. So with wonderful features of SMR and with all these practical applications of SMR, just the very beginning actually started 30 years ago. And now we have development, especially CNC have developed our series, which includes not only ACP100, but also another, what we call DHR, for just for heat supply, and as well as the high temperature reactor, as Dr. Sun has just presented. So all of these small modular reactors in China, that most of them are pressurized autoreactor, and most of them are with implementing what we call the integral design. I'll explain it later. And also this what we call the integral design is what we would say the state of the art. It's proven technology with the demonstration project. This ACP100. So it's based on 50 years experience of reactor all over the world and small reactors and our own experience for more than 30 years. And the preliminary design was completed in 2015. So it's more like 6 years ago. And we are adopting what we call the passive safety system with the integrated reactor design technology. And the design is from 2010 to 2015 for 5 years. And it is used with the concept of what we call modular design for the quality control, as well as shorten the construction period. So at the very beginning, we have certain special demonstrations for technologies. This is start line. And then we finalize the general design, or what we call the top design. And we dated our design after the Fukushima accident. We finalized our preliminary safety assessment report, which is a sign of the accomplishment of the standard design. And we finalized the preliminary design of the demonstration project in 2016. 2014, which is 7 years ago. And we have finalized what we call generic report of safety review by independent third party, the IAEA. This is what we say, how to start the design and to help finalize it. And with the promising certification, or with the independent third-party review. So this is what not we are saying, we are the good design, but by the other experts say your design is feasible, is engineering proven. Let's come with the main design parameters. The most important thing are here, like the electrical power. So it's more than 100 megawatts, and the design life is 60 years. So it's long enough and it's economic feasible. And the refilling period, the design refilling period is 2 years. So more using time, less outage. And we have our own fuel supply, what we call CF3. So there's no worry about shortage of that. We are really good at making things. And also, we have our unique technology, what we call the once-through steam generator, which are promising of the high efficiency, as well as one really important feature to have this integral design, as well as this hand pump. Another thing is not here is that we have less than 1×10⁻⁷ predict core damage frequency, as well as 1 magnitude nova, that is 1×10⁻⁸ per reactor year of these predicted large release frequency, which is this frequency is similar to a star hitting the Earth with dramatic disaster. So it's really electable because of all engineering optimization and with the design change of all the experience from the Fukushima accident. So the safety is guaranteed. And this here is what we call the integral design. The conventional, the very first generation of PWR started from this, what we called loop type. And then we go further into the compact design. But we do believe the most feasible and most advanced is the integral design. We eliminate the LOCA, the loss of the coolant accident, the most serious accident for PWR. We practically eliminated it by this integral design for large LOCA. And this is why its safety is guaranteed based on innovative technology of once-through steam generator, as well as canned primary pumps. Yeah, what you can see is not the integration is by the steam generator as well as the pump. The key technology for safety, for better operation. Another one is not what we say, the most important thing of a reactor is it's a reactor core. And these are all our own patented technology. Is the CF3 most advanced CF3 fuel, as well as the core monitoring co-detection system. And as well as the safety, we have here the integral and passive safety. I'll come further with that. So there's no active emergency cool cooling system. There's no active, we don't need it. There's no active containment spray and recirculation system. There's no shared ones. There's no need for operator intervention for at least 72 hours. That is 3 days. Enough for all kinds of recovery that you can have. And there's no safety-related emergency AC power. So we just need some of the batteries. And the integral design minimizes both the probability and impact of design basic accidents, as well as we do have a much more smaller emergency planning zone. And this is the technical feasibility for putting a reactor near the center of a population zone. What we have, some of that I have already mentioned, the elimination of large breakwater, reduction of small breakwater, the increased safety margin, as well as inherent safety by natural circulation of the primary system. Also, that coal coverage is guaranteed by coal makeup tank as well as the accumulator. This is same for all passive safety designs. But here we have natural circulation between the core and the cavity, as well as the heat conduction to the large pool outside of the containment. That is the guarantee, that is the most promising ultimate heat sink. And this is exactly why we can have 1 magnitude nova for the core damage frequency, as well as the large early release frequency. Because of the sounding safety of ACP100, we have now less non-residential area as well as the planned restricted zone. And actually, we have the guidance from the safety authority, the NNSA, what we call the National Nuclear Safety Authority of China, that the guidance now allows you, of course, under strict circumstances, that if your technology is advanced enough, that the restricted area could be less than 100 meters. Also another part, especially after the Fukushima accident, or we talked a lot, is the severe accident. And we have all dedicated system, countermeasures to cope with all expected phenomena of the coal melting, high pressure coal melting, hydrogen explosion, as well as the melted coal within the reactor vessel. All this design is reviewed by us as the generic reactor safety review, organized by the experts from IE. And why? Why we could pass that? Why we could pass this third-party independent review? Because we have done experiments. We have demonstrated feasibility, demonstrated this technology by experiment, not just by design. We have shown them these are consistent to our design. And these are the most important ones, like the control rod, the fuel assembly, the activation of the passive heat removal system, as well as the passive containment heat removal. And all these takes really long time. Some of them 2 years, and some of them even longer, years. What you have seen here, these are all the experimental facilities, but just some of them. What we call accumulation of experiments, know-how of your design. Why we are so confident of our design, why we are so confident that they are good. And of course, another part is for the equipment. Not only to prove that our design is feasible, but also we have to prove the design of the equipment, the manufacturing of the equipment is not only reliable, but also economic feasible. And also we have done that now. And this is the final design, what we call one reactor, one turbine design. And this is the final specifications for the demonstration project. And this is where it's located, also on the island, the Highland province. And here is the site. And actually, this is a nuclear power base consisted by ACP100, our demonstration project. Also, a larger one for 2 of Hualong 1000, and also 2 of 6, roughly 600 megawatts already in operation. This is just nearly 1 month ago for the construction site. We are actually a little bit ahead of our original schedule, and we are trying our best to have the first is Hualong 1000, the second nuclear demonstration project in the world that for the demonstration project that will be ahead our original schedule. We're fighting for that, but we are quite optimistic to see that in the coming years. And after this demonstration project, as I've shown you the multiple applications, that we are still looking for more projects in China for the power and heat supply, for floating nuclear power projects, for CO2 desalination, that all these are in progress. And we also have international potential customers that are interested in this technology. And all these communication organized by CDEC. And thanks to Mr. Huang and his team, they have devoted a lot. So, as last but not the least part presentation today, I would like to share you with one story, my personal story, that when I was very, very young, like 5, 6 years old, and we have these comic books, and one of that is nuclear power. Yes, about the fusion technology. With this power, we can have the resources cheaply enough for the whole world as the most bright future. And as also as for CNC, just this year, we have finalized, we have started our demonstration projects, and which in that comic book, when I was so young, said this technology is 50 years ago, is 50 years away from us. And when I grow up, when I take my job as a nuclear engineer, always 50 years away from us. But this year, 2021, we say we are now only 40 years away from our sun, from the ultimate nuclear power source. Nuclear, as we all know, is the most mighty power we have so far, but this is also quite of the toughest power source if we try to push, because of the concern of the safety, because of its technology is so advanced. We need a lot of developments as well as the infrastructures, the fundamental researches. But I do believe this is the most, maybe the only practical solution for us if we are still living on the earth. We are now facing the challenge of COVID-19. We are actually also facing the challenge of providing safe, clean, and environmental friendly energy source to our people, to all over the world. And I believe ACP 100 is one of the solution, maybe the most promising one. And thank you all. Thank you.
Okay, thank you so much, Dr. Breen, for the informative and very excellent presentation, I think. We have 7 questions for you here in the chat box. I'll try to read it one by one, I think. And the first one is coming from Professor Jarod Sulistyo Wisnubroto here. The question is, small modular reactor or SMR here hold a lot of promises for the future, including the ACP 100, but they face important hurdles. Securing financing for SMR is one of such challenges here. How does the CNNC find a solution to make SMR, or especially here ACP 100, more attractive from the economic point of view here?
Perfect. Yes, that is really interesting question, and actually has been discussed a lot, through recent years. And my personal perspective is that there are three things we need to further develop, and specifically develop for SMR. The thing is not the application. To choose your market. So normally saying, if we would like to deploy this small modular reactor in China, for example, in northern part, our marketing strategy is to take heating first ahead of power generation. So that's the first thing, to choose your application according to the expectation of its economic outcome, because the heat is much more expensive in the northern part of China compared to the power generation. It's more economically feasible for the deployment of SMR. The second thing is that you need a good team for you to develop a more detailed plan of the schedule, including the review of design, as well as the construction, as well as, for example, if we don't have the capability of nuclear fuel manufacture locally, then how is the most economically feasible option for me? Nuclear fuels. We need a detailed plan. And third, is to have an optimized financial plan, which includes not only where I can get money, but also how I could invest money. Is a blueprint to see a nuclear power source as one part of a more general plan for the development of the nuclear industry locally, according to the strategy, well, as your requirement. And I would like to bring CDEC, especially Mr. Huang and his team. They are quite experienced in that, and you can always consult with them for these three parts. Thank you.
Okay, thank you so much. Three points here. Choose the application, have a good team, fuel manufacturer, for example, and optimize the national plan, clear blueprint, for the contribution of nuclear energy here in national scheme, for example, sort of like that. And the next question is actually a bit related with the Professor Tarot's question from Dr. Suparman here. From an economic standpoint, can the ACP100 compete with the large nuclear power plants? Dr. Bin.
Sure, yes, but the most important thing is that not to answer this question generally, but as I have presented it, you must find your own market. That we do not, the large nuclear power plants, they don't fit in. They cannot practically fit in for example, small electricity grids on islands, on a very flexible siting condition, as well as multifunctional applications like heating supply. Yeah. Market that's not fitting for the large nuclear power plants. This is exactly why we left the small modular reactors. Thank you.
Great, thank you so much. So the point here, it's how to choose the market, and it depends on market, I think, actually the price. And the second question also from Dr. Suparman here. You explained that the ACP100 can be built in a densely populated area. What is the safe distance or exclusion zone, for example, here for the ACP100?
Already the safety. Is that the question from
Dr. Suparman? It's about EPZ, for example. So
actually, I'm looking all the questions from the chat.
okay.
Yes. Is that from?
Yeah.
Sorry.
Actually, after Dr. Suparman, he has two questions. The first about
okay.
Yeah. The second one
about
business.
Okay.
I combined his questions.
Thank you. So yeah, thank you so much. Actually, from the latest guidance of our own nuclear safety authority, that under, of course, very stringent circumstances, which you have to prove your safety, and for really stringent circumstances. But it's, if you are good enough, the safe distance can be shortened to 100 meters. 100 meters. Okay? So this is a breakthrough for the deployment of advanced small modular reactors.
All right. Thanks, Dr. Vince. The next questions from Ms. Gainirina Sunario here. How is the very recent status of the constructing ACP100 compared with 2019 on IAEA SMR technical meeting? How is the strategy to suppress the electricity price as first of kind construction?
Yes. Thank you. This especially the next question, the second question is very interesting. Okay, we start with the first one. The recent status of this ACP100 demonstration project, we started the first concrete dump at very beginning of this year. And as I have shown you with the picture just 1 month ago, so all the constructions on site are going very well, going smoothly. Actually, a bit our original schedule, and we are quite confident that our ACP100 demonstration project, the very first SMR in the world, will also be ahead or consistent to our schedule. And this also is related to your second question, how to suppress the price, how to lower the cost, and why we can be consistent with our original schedule. The most important thing is to use proven technology. Use of the proven technology is very depending on the capability of your design team. Material design is quite new design, but how to combine an innovative design with proven technology? You need first-class design team of the world. We are proud of them. Thank you.
Okay, thank you, great, Dr. Vince. Let's move on to the next question from our senior researcher here from the safety divisions, Mr. Sony Cahyadi. What is the largest contribution of the initiating event to CDF or coordinate frequency of ACP100?
Thank you. This is also a quite interesting question. Actually, we have implemented the probabilistic safety analysis at the very beginning of our design. So we have actually optimized some of the designs according to the result of CDF. It means the contribution of all these initiating events are quite similar. There's no one or one category of the initiating events like contribute, like as the contribution of taking more than 20 or even more than that. So there are like tens of the initiating events, and most of them just taking around 10% of the total CDF. Some of them, I do believe you are quite familiar. Some of them are the loss of the coolant accident, because this is a PWR design, of course. Some of them are the reactivity accidents, not leading to the core damage, but still have the consequences on the or partial core damage, not the core melting, but the break or the loss of the integrity of a few of the nuclear fuel assemblies. Thank you. If you would like to have more details, we can discuss later.
Yeah, perhaps Mr. Sony will contact you further if he has more detailed question about the coordinate frequency. He is an expert in here. Okay, the next is from Mr. Deputy, Mr. Suryantoro. ACP100 is a demonstration NTP. That means it's first of kind, or FOK. How much the CNNC prepared budget for it, and how about the NOK, number of kind, later on, the cost?
Wow, this is a quite challenging question, because this is, this is a commercial.
But you should go with the number.
Doesn't matter. We are friends. I can tell you the rough ideas. The rough ideas here is that. So the first of these kinds target is around $3,000 per kilowatt for its construction, okay, for the cost. It's roughly around that. And we are actually trying to, which is quite ambitious, but we are trying to reach a goal for the deployment to lower the cost to near $2,000 per kilowatt. We're trying for that. And we really do believe that target is very, very competitive. All designs of SMR is proven technology.
Okay. So about 3,000 kilowatts for first of kind, then going down to 2,000, about that, yeah? For end of a kind.
Well, yeah, we're trying for that.
Yep, okay. The next one is from Mr. Tukiran Surbakti, is from the Center for Nuclear Technology and Safety as well. Next presentation, Dr. Vincent. If I'm not mistaken, you said also, or you develop a floating nuclear power plant using the ACP100S, the variant of CNNC designs, a marine version of ACP100. Could you tell us a little bit the design of ACP100S? You have a research collaboration with another country? Yeah, he's asking about the collaboration research as well.
Sure.
Please.
I'm really happy to answer your question, sir. Or madam.
Sir.
Oh, okay. Okay.
He is a senior researcher actually in my division.
Thank you. Okay, thank you so much. Sir, the design of ACP100F for floating nuclear power plant. The nuclear steam supply system and the most essential part, the reactor, is exactly the same as ACP100. And this is what we call the modular design. So you use just one kind of this design, but for all different kinds of applications. And this is exactly why we can lower the cost. And as for the research collaborations, actually CNC we are always open to international collaborations. So that's not for one country, that's actually for many countries, and as well as international organizations. Actually, I do believe we have one of the pilot projects actually with, if I'm not mistaken, with Barbiton, like roughly 10 years ago. Not for the floating nuclear power plant, but for the design as well as safety analysis of nuclear reactor. Yeah, and we are happy to see more and more collaborations with you and with other partners. Thank you.
Okay. Thank you, Dr. Vince. Yeah, I believe that Dr. Tukiran, I think, is not really satisfied with your answer. I think still need a lot of explanation about the SCP-100S, but it's okay. The time is limited for us, actually. We move on to the next question from the Waste Management Center from Mr. Gustri. Do you have any data regarding the amount of radioactive waste product produced annually from SMR?
I do have, actually, we have several different models, and especially for the design of the waste management of ACP100, we have optimized it with the most advanced technology for the reduction of its quantity as well as its volume to minimize the radioactive waste management, the burden of that. And I do have several rough models. Actually, they are also referenced in the IAEA publications. If you would like to know more details, I can send you some of the reports from IAEA, open reports, for your further investigation.
Great. Okay, thank you. Probably you can send the data after this. What about the waste as well? And I will pass it to colleague from Waste Management Research Center, if you have any further detail about that. And then the last one here from Mr. Arbi Dimyati, how long do you need to do research on ACP100 from the beginning? And how long to build it until the operation on the beach? Yeah, I think you've mentioned it before, but please fill again.
Sure. As for our experience, development, and as also I have shown in the presentation, the development, especially most of the time, is used for the verification and validation by experiments. The whole R&D took 5 years, but on the 5 years R&D is based on the accumulation of our engineering experience, as well as knowledge, as well as teams, engineers there for more than 30 years.
Okay.
Most valuable things, yeah. And
okay,
to build it, it takes now roughly 48 months. It's roughly 4 years. Yeah.
Okay, that's pretty good, I think.
Thank you, sir.
Yep.
And sorry for my time.
Yeah, that's fine. You got a lot of questions here. That's fine. You've clearly answered everything. Hopefully, if anybody's here need more detail about the answer, you may email us or just write down here. I will pass it to Dr. Tin here after this event. Okay, ladies and gentlemen, it's conclude the Mr. Chen Bin presentation about ACP100 by CNNC, the concept and design principle, technical feature, and also demonstration project. The next presentation, I will hand over again to the moderator, Mr. Huang Yuliang, to introduce the next presenter.
Okay, thank you, Dr. Xiaofu. And we just had a very fruitful discussion on the different types of SMR, especially HTR and ACP100. Then we will switch to the large-scale PWR, the third generation design, and in which we have the 100% self-intellectual properties, the HPR1000 technology. So we are very pleased to invite Mr. Zhao Huixia from China, for the Nuclear Power Engineering Corporation, for the General Design Division. He is very experienced in the design and development of HPR 1000, especially for the demo project and also the forthcoming project located in Zhangzhou. So Mr. Zhao, you have the floor. Thank you.
Good morning, ladies and gentlemen. It's my great honor to have this opportunity to introduce our HPR 1000 technology for you. And first, I would like to test the sharing on my screen. Okay. Video and the voice both okay?
Yeah,
it's okay.
都能听见吗？
都可以。
好。Okay, let's start. My name is Zhang Huixia. I'm from the General Design Division from CNP, the China Nuclear Power Engineering Corporation. We researched and developed the HPR 1000 technology through many efforts. So it's my honor to introduce our HPR 1000 technology for you. According to the agenda, the design principles, technical features, demonstration project, and the latest progress of HPR 1000 will be introduced in my presentation. First, the design principles. In fact, Many aspects of design principles are applied in the R&D of HPR 1000, like proprietary IPR, safety, economy, maturity, site adaptability, and localization. But in this presentation, it will mainly focus on the design principles of the aspects of nuclear safety. The HPR 1000 design follows the defense in-depth fundamental principles. And this is one of the most important principles in MPP design. And then the redundancy, diversity, and independency of SSCs have been improved significantly to ensure the reliability of the safety items. And last, integrated application of active and passive safety measures for prevention and mitigation of accident. And the active measures mainly for the design basis accident, and the passive measures mainly for the design extension conditions, including severe accidents. All these principles will be introduced detailedly in the following slides. And here some detailed description of the principles. For the defense in depth, we enhanced the safety configuration, especially safety features of level 3B and level 4 for DC or design extension condition. The level 3B for Decay without core melt, and the level 4 for severe accident, Deck B or with core melt. And these levels of defense in depth are as far as practicable independent. For example, the level 3 and level 1 for normal operation, and the level 4 for severe accident. And then the redundancy. The safety systems for level 3A for DBAs fulfill the principle of redundancy and the single failure criteria, and the critical active equipment for level 3B, also Decay, are considered. And for diversity, we apply active and passive safety design philosophy for all the accident conditions. In equipment level, for example, we use motor-driven and turbine-driven pumps in the auxiliary feed water system to remove the decay heat from the reactor core, and also in many other aspects, such as the power source and sea and ultimate heat sink in the design. For example, the ultimate heat sink, different heat transfer links, chains, either from the seawater or the outer atmosphere. And at last, the independence. For redundancy trains, we put them in separated buildings or rooms to get the physical separation. And for safety systems and the normal operating systems, we do not use the same equipment sharing between them to get function separation. And also for electrical and sea and communication separation according to nuclear safety codes and standard requirements. And the second part is the technical features of HPR 1000. First, let's take an overview view of the HPR 1000 design characteristics. It satisfies the latest nuclear safety codes and the standard requirement, both from China or IAEA or other international organizations. And it also fulfills the utility requirements for advanced light water reactor like EOR or URD from Europe and the USA. Also, it integrates the feedback of Fukushima accident. We set interfaces for several kinds of mobile equipment in extremely severe conditions. And our HBR1000 is an evolutionary design based on proven technology. So all this make it a safe, reliable technology with economic competitiveness compared with other generation 3 PWR NPPs. Then the general parameters of HBR1000. First, the reactor core thermal power is 3,180 megawatts, and the nominal electrical power output is about 1,200 megawatts, maybe a little different according to the different site conditions. And the design plant life is prolonged to 60 years compared to the generation 2 commercial PWR MPPs, and the refueling length of 18 months, and the plant availability more than 90%. And these make HBR1000 more economical. The peak ground acceleration of the SSE, the safety shutdown earthquake, both the horizontal and vertical directions are 0.3 G. So it enhances the site adaptability of HBR1000 for different site conditions. And also the load follow capability to provide more operation flexibilities, and depend on the excellent safety performance of the safety features. The operator non-intervention period is 30 minutes, and the plant autonomy period is 72 hours. And according to the PSA calculation, the CDF is less than 10 to minus 6 per rate year, and LRF less than 10 to minus 7 rate year. So it satisfies the requirement of the latest codes and standard, also the generation 3 PWR NPPs requirement in different utility requirements. Then let's see some detailed design information for the detailed design. First, the reactor and the primary system. The reactor core consists of 177 field assemblies with lower linear power density to ensure sufficient core thermal hydraulic margin. And we have two reactivity control systems. One is control rod and the other is boron. So they both ensuring the reactivity control functional capability and reliability. And the refueling cycle of 18 months and load follow capability, as mentioned in the last slide. Then the field assembly, we use the independent CF3 assembly with an innovative advanced cycloid cladding material N36 and the designs of the grade nozzle and guide tube. And it's composed of 264 field rods arranged within a 1717 supporting structure, and the performance and the burn up satisfies the refueling cycle of 18 months. Oh, then the primary system of the reactor coolant system consists of a reactor pressure vessel containing reactor core and core internals, and based on a mature 3-loop design, each loop contains one reactor coolant pump one steam generator and main pipes between them. And at last, the one pressurizer and the surge line are connected to the main pipes to control the pressure and temperature of the system. And then the design of buildings and structures. The nuclear island building is with single unit layout. The benefits of this layout can provide physical separation, reducing the interactions between different units compared to the traditional PWR MPPs. And it's very convenient for plant construction, operation, and maintenance. And it's also more flexible for plant siting. And this picture shows different nuclear island buildings of HP 1000. In the center, the reactor building, and around them, electro building containing MCR, main control room, and the fuel building. And in the opposite side of the reactor building, the two separated safety guard building, and also in other sides, the access building, nuclear waste building, and nuclear auxiliary building. For the reactor building, the design of the containment with a double shell containment, the inner shell of it is built by pre-stressed reinforced concrete with a leak-tight steel liner inside, and the outer shell with a reinforced concrete structure to protect the inner shell from the outside hazards. And the annular space between the inner shell and the outer shell keeps the negative pressure of it, and so collects and filtrates of the leak from the inner shell during normal operation and accident conditions. And the containment have a larger free volume of about 87,000 cubic meters. So it reduces the pressure during accident conditions. And lifetime is prolonged to 60 years, consistent with the plant lifetime. And this design of the containment can withstand external events, including large commercial aircraft crash, tornado, missile explosion, and so on. Detailed, the enhanced capability of protection against external events, especially on earthquake and aircraft crash. As mentioned before, the seismic input with peak ground acceleration is 0.3 G to have a better site adaptability. And for aircraft crash, the protection against large commercial aircraft crash, we have APC shell, anti-plane crash shell protection for reactor building, fuel building, and the electric building, containing the main control room. But the safety guard building containing redundancy systems are not protected because they are put in opposite side of the reactor building. So they will not be damaged in the same time. Then the safety design philosophy of the safety systems, both in DBCs and DCs, we use the active plus passive safety design of these safety systems. The active measures proven and verified based on mature design of the traditional PWR MPPs, and the passive ways need no AC power, so they provide reliable and powerful additions to the active safety features. Well, the active plus passive safety systems provide diverse approaches to perform the safety functions of emergency core cooling, core residual heat removal, and cavity flooding and cooling to change the investor retaining and containment heat removal. First, the engineered safety features for DBA in defense in-depth level 3A. We have 3 main engineered safety systems. First, the safety injection system for emergency core cooling, and the containment spray system for containment heat removal, and auxiliary feed water system for core residual heat removal from the secondary side. And then the safety features for multiple failure in defense in-depth level 3B, also called Decay. That means deck without core melt. We set several kinds of safety measures to cope with different typical multiple failure modes. For example, we use an emergency boron injection system for ATWAs, and SBO diesel generators for station blackout, and diverse cooling chain, both active ones and passive ones, to cope with the loss of ultimate heat sink, and diverse actuation system, or called DAS, to cope with common mode failure of protection system, and passive containment heat removal system for loss of containment spray system. And last, for the defense in depth level 4, deck with core melt or severe accident, we have several countermeasures for different severe accident phenomena. For example, the fast depressurization system for high pressure molten corium ejection to prevent direct containment heating and induced SGTR, and cavity injection and cooling system to prevent basement melt through by the RPV bottom head failure if the core melt down, and passive containment heat removal system and containment filtration and exhaust system to cope with prevent the long-term overpressure of the containment. And at last, the containment hydrogen combination system to prevent for hydrogen detonation. We also learned many experiences. So we take these Fukushima feedbacks as additional emergency measures for extremely conditions beyond our design envelope. For example, we set additional emergency water makeup and associated interfaces, and improves temporary power supply with SBO generators and mobile generators in extremely severe conditions. We enhance the radiation and hydrogen concentration monitoring under the severe accident, enhance the spent fuel pool monitoring and cooling capability, and the seismic and flooding design is more conservative margin. And we also enhance the habitability and availability of the emergency facilities. Here are some detailed information provided for the water makeup, the portable equipment and interfaces from the primary loop, the secondary loop, and spent fuel cooling. We can use mobile pumps and fire engines to provide water makeup to these systems from varieties of water source in and out of MPPs according to the site conditions. And then the design of HPR 1000 is based on the proven technology. The NTRPS, the nuclear steam supply system, is based on mature design, very similar configuration with operational experience of more than 1,000 reactor years. And most advanced features is based on experience of previous MPPs and new features verified with experiment. And main equipment is compatible with mature manufacturing capability with proven quality, reliability, and maintainability. And then the design solidified for demonstration project, and we passed the independent safety reviews of different organizations. First, the proven and verified technology. The configurations and the operation of the normal operating systems and the active engineered safety features have been validated by long-term engineering practice from existing PWR MPPs. And the design concept and the technologies adopted for passive safety systems have been verified by natural science or specific experiments or tests. And the manufacture and supply capability of almost all equipment and components is compatible with the existing MPPs, and benefiting from rich construction periods and outstanding feedback of operating experience of China. The construction period and performance of HPR 1000 can be ensured. And some detailed information and pictures for the mature design of the primary loop. As we mentioned before, the main comment, the reactor pressure vessel, steam generator, reactor coolant pump, pressurizer, and all based on the mature three-loop design of the PWR MPPs. And the verification tests and experiments for new applied technologies, especially for the three main passive safety systems for the design extension conditions. For example, the test for passive residual heat removal system for the secondary side, the PRS system. The test for the passive containment heat removal system for the PCS system, and test of the capture injection and cooling system, the CIS system. And the proven equipment. All the key equipments are based on the mature technology, and the equipment are compatible with existing manufacturing capabilities. During the design of HPR 1000, we passed several independent reviews. For example, the independent review by NASA from Argentina, and the general design was approved by NEA and NSA of China government, and the basic design was reviewed by the CNEA, the China Nuclear Energy Association. And the safety review for the demonstration project, the Fuqing Unit 5 and 6, and the Pakistan Karaj Unit K2 and K3. The PISA for Fuqing Unit was reviewed by NSA, and the PISA for Karaj K2 and K3 project was reviewed by the PNRA of Pakistan. And we also submit the generic reactor safety review report to IAEA in December 2013. And in 1 year later, the IAEA issued the review report with a positive comment. And we also enjoyed the MDEP program. The HPR 1000 work group was established to focus on the safety review of HPR 1000 design and achieve common technical opinions. Then the third part, the information of the demonstration project. First in China, the Fuqing Nuclear Power Plant Unit 5 and 6. This is the bird view drawing of the Fuqing NPP. The first 4 units are with a reactor type of CMP 1000 generation 2+ reactors, and the unit 5 and 6 are HPR 1000. The FCD type was on the May 7th, 2015. Here are some photos of the some important milestones of Unit 5 of Fuqing NPP, the FCD and the containment dome installation. And the latest progress of Fuqing Unit 5, the first grid connection was in November last year, and the demonstration run lasting 168 hours was completed this year in January, and it began commercial operation 1 day after that. Now, the Fuqing Unit 5 has been running safely and steadily at the full power since it entered commercial operation, with the exception of the Spring Festival peak regulation shutdown during February. And until now, there are no unplanned outage and unplanned forced power reduction. That's a very outstanding performance compared to other Generation 3 PWR MPPs. And here are the progress of the second unit, Unit 6 in Fuqing MPP. FCD was also in 2015, about half a year later than Unit 5. And this year, in January, the code functional test was completed. And in July, the inner containment integrate test has also been completed. And the project safety and quality is well under control, and the unit is scheduled to begin operation by the end of this year. Now, the first 2 HPR 1000 exported out of China in Pakistan, Karachi, K2 and K3 units. Just behind the Fuqing Unit 5 and 6. K2, the FCD was on also the 2015 in August, and initial fuel load last year in December, and in this year in March, the first grid connection and the formal inauguration ceremony was held by the Pakistan Prime Minister Imran Khan in May. And the second unit, the K3 FCD, was 1 year after that of K2. And this year, in April, the code functional test was completed, and the overall progress difference between K2 and K3 is about 12 months. And until now, the construction progress is well under control through effective project management as well as effective local participation. Then the last part, the latest progress of the subsequent units of HPR 1000. And these picture shows the NPPs in China now. And the HPA 1000 is in these three sites: the demonstration project, Fuqing NPP, and the first two subsequent projects, the Zhangzhou NPP and the Changjiang NPP in Hainan province. And until now, the successor optimization is still going on for the design and research of HPA 1000, mainly from these four aspects: the latest safety requirements of the codes and the standards. For example, the latest version of nuclear safety codes and guidance of China, and also the feedbacks from the demonstration projects, both from Fuqing and Pakistan. And the design optimization is based on the feedbacks from the utilities, and also optimization to reduce the cost, shorten construction period, so as to improve the economy. All these optimization for the future HPA 1000 projects for batch construction. For the first subsequent project, Zhangzhou NPP Unit 1 and Unit 2 project, the first following project for the HPA 1000 batch construction. About 50 design improvements will be implemented, with other nearly 100 design optimization based on the utilities feedbacks. For example, the main improvements adopted by Zhangzhou NPP Unit 1 and Unit 2 project. First one, the further improve the safety to meet the latest safety requirements for licensing. We take comprehensive analysis for the design extension conditions from the latest codes and the standards, and also the design improvements for the diverse actuation system. Use different platform softwares compared with the DCS and the processing system. We also adopt the safety classification principle based on the IA SSG 30, the newest guidance of the agency. The second one, improve the plant economy and operational performance. The power is escalation to 1,200 megawatts, and we use the medium voltage level from 6.6 kilovolts to 10 kilovolts for electrical system. That's for the localization of China. And the improvements on waste treatment system with some new processing technologies to process the waste. And also the design modification to shorten the construction period and benefit the construction efficiency. For example, the main equipment installation on the position before reactor building capping, and pre-installation design modification for the stainless steel liners. And especially for the Zhangzhou NPP Unit 1 and Unit 2, the general progress for Zhangzhou NPP. First one, the project approval and licensing. The project approval was obtained April 8th in 2019, and the construction permit is issued by NSA in the same year. And the engineering and on-site progress now, The preliminary design has been solidified, and proceeding detailed design issued. Construction drawing documents satisfy the on-site progress now. And here are the latest progress for Zhangzhou MPP, and some photos from the site. FCD for Unit 1 and Unit 2 in 2019 and 2020. And now the whole site was under civil construction stage, and the design, procurement, and the construction progress is well under control according to the schedule. And also some other projects after Zhangzhou. First is the Changjiang in Hainan Province, Unit 3 and Unit 4, the same site as the ACP100, the SMR. The project approval was obtained in 2020 last year in September, and this year in March, the Unit 3 FCD. Now it is also under civil construction stage. There are two photos of the Changjiang MPP site. And also some other subsequent projects are undergoing now. For example, the Pakistan Chashma Unit 5, the general contract has been signed, and the preliminary design and the PISA was initiated. And Zhangzhou MPP Unit 3 and Unit 4 is in pre-site preparation phase now. And these are all the latest progress information for the subsequent HPR 1000 units. And that's all. And thanks for your attention.
Great. Thank you so much, Dr. Jiang, for the presentation. Very informative, I think, and comprehensive as well. Okay. We had 4 questions for you here. The first one from Mr. Deputy, Mr. Suryantoro, is pretty straightforward here. The question, how about the cost of first of kind, the cost of end of kinds, and the time for construction, please?
Excuse me, I'm not very familiar with economy affairs. What I mean by full or no cost?
The first of kind cost, the first construction perhaps at that time. And now I believe you've constructed the ACP 1000 or HPR 1000 here for number of plants. Don't you? Yeah. And then
I will check that number of plants. In my impression, the cost of the demonstration project of HPR 1000 is about, I think, about $2,000 US per kilowatt.
Okay.
And the time for construction in the presentation for the Fuqing nuclear power plant Unit 5 had already entered the commercial operation. Its construction time from the FCD to former commercial operation is about 68 months from the May in 2015 to January this year. And I think in the subsequent projects like Zhangzhou or Changjiang or the Chashma Unit 5, because of the feedbacks from the demonstration projects, Fuqing Unit 5 and 6, the Karachi Unit K2 and K3, we can make it shorter. Our goal may be 60 months, about 5 years, or even be shorter.
Okay, great. So the cost is still $2,000 US per kilowatt, or any decreased cost after several units deployed?
I'm sorry, because I'm not very familiar with cost things.
All right, yeah.
Majorly the safety design. So I will record these questions and I will check these informations and maybe send to you after from the CZAC.
All right, no worries, that's fine. Okay, let's move on to the question from Mr. Hadisun Toko. He's part of the site preparation engineer over there. I think he's asking about the civil structure. Question for Mr. Jiang. How many weight of the reactor building, the first building?
How many weight about the how many tons or
yes,
kilometers?
How many tons? About that, yeah, approximately, yeah. Yes.
Because probably, we never talk about the we never talk about the weight of the reactor building. So
all right,
I'm sorry, I really don't know that weight. Because I can check with my colleagues of the construction specialty.
Okay, great. That's fine. He's probably asking about the weight because he's concerned about the site's capacity, how to support the reactor building overall. Okay, then let's move on to the question from Pak Abu. Thank you so much for the very interesting presentations. Mr. Abu is Dr. Abu is the researcher from the Center of Advanced Material. It is mentioned that the HPR 1000 use zircaloy cladding material or N36. Could you give further explanation the superiority this material compared with zircaloy 4 or the other perhaps? Thank you. Please.
Okay, very difficult questions that really got me because I'm not a specialist on the fuel assembly, so I can just record this question and to send this to my colleagues and for their help. I'm sorry.
Okay, that's fine.
That's very difficult question for me.
Sorry, Pak Abu. Yeah, he will answer it later on by maybe Dr. Jiang, please email me the answer, okay? Yeah, I'll talk to Mr. Teddy after this. The second one from Mr. Abu, Dr. Abu as well. One more question. Could you explain the safety scenario for the SBO or station blackout accident of HPR 1000? Yes. Please.
The safety scenario means the accident scenario after the station blackout occurs. Because in normal design basis accident, we have the EDG, emergency diesel generators, for the active engineered safety systems for different accident scenarios. But if the EDG fails, so the station blackout occurs. So to cope with these conditions, SBO or the Decay design extension conditions, we set the SBO diesel generator to cope with this condition. And in this condition, the active engineered safety systems cannot be used. So we use the passive ways and also some dedicated safety features for the SBO. Maybe we can check with, I was sharing my screen to the slides about the SBO. Okay, yeah, that clear. For the station blackout system, we use SBO diesel generators And this is for mainly because its capacity is not so large as the EDG. So it's mainly for the PAMAS, the post-accident monitoring system, and some sensors and INC system, and some low power systems and equipment. For the primary system, the heat removal is from the PIS, because the auxiliary feed water system of the active waste can be used, and we can use the turbine-driven pumps to remove the heat from the secondary side of the reactor. If this fails, we can use the passive cooling system from the secondary side. And also the we have the standard CLC of main pump. So we can use a hydro test pump to maintain the volume of the RCA system. And if that fails, we use the standard CLC of main pump to maintain it. The load cannot occur in the RCS system.
Okay.
Maybe not. My expression is not very clear. So overall, we usually use the passive ways in the SBO conditions, but with the diesel generators, we can use some low power equipment to transfer the heat from the safety systems. And also the diverse cooling chain in this, because the engineered safety fuels can be used, so we can use the SBO to support the dry cooling unit from the WEC system, what's the name? The cooling chain units to transfer the heat from the electrical and INC system. But I'm sorry, we don't have a very detailed slide just for the SBO conditions, because it is connected to many safety systems.
Okay, that's fine.
After this meeting, I can provide some more detailed information and the description about our measures to cope with the station blackout conditions.
Okay, thank you, Dr. Chiang, for the answer. I believe that's for the future. I think we still have, we can have a further discussion, especially for Mr. Abu or gentlemen already here about the safety of HPR 1000. Okay, ladies and gentlemen, that's the conclude of the session for HPR 1000. Talk about the future, the licensing, and about the demonstration projects. And for the concluding remarks, I'll hand over to Dr. Huang. Dr. Huang.
Yeah. Okay. So just therefore, thank you for monitoring this interesting thematic discussion. And as you mentioned, now we reached the end of the first day seminar program. And today we are very honored by the presence of the leaders and the director from both sides, especially Mr. Dino from the Indonesia Embassy to China. And we are using this half day to discuss three main nuclear power technology of CNC, including 2 SMR technology and 1 PWR large-scale technology. These are all the most advanced technologies used and will to be largely deployed in China and worldwide. So I think both sides, we have after presentation, the experts and also the attendees from Indonesia part have a very deep exchange. And maybe for some further technical details, as experts mentioned, we will give you more documentation and technical support to respond all the questions. And also, I think all the experts and also the CCEC team, we are available 24 to give you more supports and more details. So, Mr. CFO, that's my remarks. Thanks for your monitoring. Thank you.
Okay, thank you so much, Dr. Feng. Okay, I will hand over again this session from morning until this afternoon to Master Ceremony. Hopefully we can meet again tomorrow at the second day. We will start at 9 o'clock with another topics about nuclear technology, radiation protection, and also for research reactor. Okay, Bu Nina, time is yours again.
Thank you very much for moderators for the session and all speakers for the excellent presentation, and also all the participants for your very active participation. Finally, let's give applause for all the speakers. Ladies and gentlemen, it's a wrap for today. We will be back for the second session tomorrow. It's been our pleasure to host this event. Thank you very much for your attention. I wish you all a pleasant day. See you tomorrow.
Thank you. See you tomorrow.
See you tomorrow. Thank you, Pak Dandang.
See you tomorrow. Thank you.
See you tomorrow. Thank you.
Yeah.
Bye-bye.
Bye. Thank you very much. See you tomorrow.
See you, Pak Jupiter.
See you. Nasi boxnya ya, Pak Saiful.
Oh, siap. Nanti Pak Dadang mau kirim GoFood Pak ke situ.
Mantap ini moderator kita hari ini. Luar biasa.
Makasih, Pak. Makasih. Yang mantap MC-nya ini, Pak. MC-nya baru datang ke PT KRN langsung jadi MC internasional. Iya.
Kalau MC tiada duanya, Pak.
Bisa jadi langganan nanti, ya.
Iya. Saya izin live Pak Saiful ya.
Siap, izin juga. Live ya, izin live juga. Mas Dika silahkan di end for all ya.
Oke, makasih semuanya.
Jangan lupa direkam ya, rekamannya jangan diberhentikan dulu.
Oh iya Pak.
Yeah. Oke, mohon pamit ya.
Mari Pak, silakan.
Saya tutup ya Bapak Ibu.
Ini nggak ada presensi nih.
Sudah.
Ada Pak.
Ada Pak.
Ada Pak di chat Pak ada Pak.
Sudah Pak.